Hello, this is Josiah Winslow recording for his Data Structures and Programming course at MATC for instructor Mark Cribb. This setup that I have right here is not exactly ideal, but we'll roll with it and see how it goes. This week's assignment was on hash tables, and before I explain what those are, I have to explain a concept called direct addressing, which is where, let's say you want to have a set of keys mapped to a certain set of values in a large table. What you could do, assuming the keys are all integers, by the way, is use that key directly as an index into whatever array, and then store that value at that position in the array. Now this works for a small universe of keys, and in fact is used in, for example, counting sort to sort small lists of integers. But let's say you have really, really large integers. Integers so large that you couldn't ever hope to store all of the previous indices from 0 all the way up to that number in a big array. And let's say maybe you don't even have all integer keys. Maybe some of them are floats, or some of them are strings, or whatever else that you can't directly index into an array from. That's where hashing comes in. Now, a hash function is any function that will take a value of any type, really. It can be any type of an arbitrary length, and it turns it into some integer that is of a fixed length, like 64 bits or 32 bits. And you can use that as an index into a much smaller array by taking the remainder of that modulo some number, usually a power of 2. That is the size of whatever table you're storing. So that's basically how a hash table works, is it takes whatever key that you're trying to store, runs it through that hash function, and then you can take that modulo the size of whatever table that you have, or whatever array that you have internally, and then store that value at that position in the array. Actually, more realistically, you'd be storing the key and the value together to make sure that there's no confusion and no false positive. And actually, there's also a little bit more that you have to do to resolve when two values map to the same index, but that will be a bridge we cross when we get there. Now, for reasons I fail to understand, I implemented my own version of it in Python, which doesn't make sense because Python already has one of these. It's called a dictionary. But I thought that I would implement a version of it myself because I find it really interesting how they implemented the dictionaries in Python, and I wanted to be able to learn how it works myself by doing it myself. So here I have a little helper class called hash element, which has a hash, a key, and a value all together, and those will be the entries that I store in my entries table. Now, what I end up doing is, and let's just go to the clear function to see all of the items we have. So, these are all the variables that my hash table keeps track of. Self.used, which is the number of slots in my table that I have used and are filled with values currently. Self.fill, which is the number of slots in my table that have ever been filled with a value, even if I deleted it. And self.size, which is the size of the table. And here I actually have two different lists. One is a list of integers, well, either integers or none, to indicate nothing. And I have a list of entries, which is a list of hash elements. Now the indices are actually going to be, instead of indices into itself, they're going to be indices into this entries table. And I'm doing that because Python has implemented their hash tables in this way as well, so it can remember, well, actually, it's so that it takes up less memory to store the whole table, but as a side effect, it also helps you remember the order in which you inserted the elements, which is a really helpful feature sometimes. So the indices that are stored in this list will be indices into this entries table, and then each entry will have the hash of the item, the key, and the value. And we store the hash so we don't have to recalculate every time. So we create the hash map and optionally update it with some sort of mapping or iterable of key value pairs and or keyword arguments. And most of these functions are really simple. I won't explain them, but I will explain the get item, set item, and delete item methods. Now, get item, what happens is we have to get an item that is stored with a certain key, and to do that we calculate the hash of that key, which Python has a perfectly good hash function which I decided to use. And this function right here, self.probe, this is a private method that I have internal to this hash map, which basically goes through a series of possible indices to place this thing. It starts at a certain particular index, and then if that's already occupied, then it goes to the next index, that it might be able to store, and that's calculated with a formula. And if that doesn't work, it goes to the next index, and so on and so forth, and eventually it'll hit all of them. So, whatever index we try to get the item from, we get that index into the indices table, and if that index doesn't exist, then there's no item here. We raise an error, or exception. Otherwise, we index at that element into the entries table, and if the entry exists, and if the entry key and hash are the same as the key and hash that we want to get, then we return its corresponding value. It's a similar thing for set item. So we get the hash of the key. Here we create a new element that we're going to be storing at this position into the entries array. We index into the indices table. If that index is unoccupied, then we store the index into the entries table into the indices table. We add that entry to the entries table, and we update these little counts, self.use and self.fill. Used, by the way, can either go up or down depending on how many entries are stored in the table, and fill never goes down, except, maybe when you rebuild the entire table from scratch, which we have to do sometimes if it gets full. And at this point, we can stop probing, we can break. And if the element does exist, if we index into that entry into the entries table, and it does exist, and if this key is the same as the key we're trying to store to, then all we have to do is replace the item. And this is something we have to do sometimes. We have to keep track of what is called the load factor of the table, which is basically how many elements it has in it, divided by the size of the underlying array or list. And here, if self.fill divided by self.size, which is the number of elements that ever have been filled in the table, or the proportion of the elements, if that is less than or equal to self.maxLoad, which I've set at a certain percentage, then we're fine. We don't have to do anything else. Otherwise, if it's over that, then we might need to double the size of the table if we've stored way more elements than we need to. And then here we call this Resize Method, which is another private method, which basically rebuilds the entire indices table from scratch. And delete item is very, very similar to the set item method, except the only difference is if that index had never been stored to, we raise an exception. We can't exactly delete something that's not there, right? And if we do find it, then we set that entry to none. Now note that we do not actually remove that entry from the entries list, because there might be entries after it in the list, and their indices would be thrown all out of whack if we actually just remove that from the list. So we set it to none, and we decrease the used variable right here. And also, I don't believe the Python dictionaries have this, but I have it such that if we are now using less elements than some threshold, then we have the size, if it's at all possible. That is, if it is still above a certain minimum size, and that minimum size I have is 8. And then we resize the table. And here we have a whole bunch of other sort of helper methods, which are also part of the dictionary item. And here we have update, which if it's an instance of a mapping, then we loop over all of its keys and values and then set that key to that value in our table. Otherwise, if it's an iterable key value pairs, we iterate it like this, and we also loop through the keyword arguments. And this right here, this is I think it's kind of clever. So the way that the pop method works on dictionaries in Python is that you can pop a certain element with a certain key. Like, you can remove it from the table and then return it. And then an extra thing that it has about it is that if you provide another argument that's the default, then it will return that value if the item doesn't exist. Otherwise, it raises an error if this isn't there. Now, the only real way to do that, make a function that does different things depending on the number of arguments you give it, there are only two ways. One is to use, I believe it's called unpacking of some sort of arguments list that you get. I'm not going to take the time to explain that because I don't think I've literally ever used it, at least in this set of assignments for this class. And the other way, canonically, to do that is to have the argument be none by default, and then you check if the element is none, or if the parameter is none, excuse me. And if it is none, then you act like it hasn't been provided. And if you don't provide a keyword argument like that, if it's going to be none by default, then it will just be none. So that, I believe, makes sense. However, none is... I wanted none to be an acceptable value here, so I had to do something a little bit different. And see, this thing right here, called marker, I have that set to a blank object. And what's cool about object is that if you have like a blank object, you can't really change it, and also it doesn't compare to anything except itself. It is not equal to anything other than itself in either an is sense right here, or as an equals sense. So this is a way for me to check whether or not the argument was provided at all. So this pop method tries to get the value of the key. Now, if we got a key error trying to get that value and it doesn't exist, then if the default is the marker, like in an identity sense, not just equal to, is actually the same object as. Then we raise the key error if the default was not provided. But if it was provided, we return it. And if the key did not, if the key did exist and did not give an exception, then we delete that key and then return the value we got. And then here we have a whole bunch of extra helper methods. And so on and so forth. And here we are at the resize and probe. And resize builds the indices list at whatever size the array is. And it takes the entries list and it actually filters out all of the elements that are none, because in deleting some of the elements, they might be none. And then the filled elements are exactly the same as the used elements because there are no elements that were deleted. And then for each entry in all of these entries, we try to probe through the possible indices to insert it, and then we insert at that index if it works. And that's how we rebuild the table whenever we have to resize it. And this is the probe method. Now, first we calculate the index by taking the hash that we give it and then doing modulo self.size to bring in a range. And one detail of how Python does their does its kind of probing is it uses something called perturb, and what that is initially that's set to the hash itself, and then that's added every time it goes through one loop of the formula, and then bit shifted to the right so that it eventually goes to 0, and that's like to give a little bit of pseudo randomness to it. So the details about how this method, how this formula works can be found in the source code of the Python language. I believe the relevant file in Cython, that's C-Y-T-H-O-N, is dictobject.c, and it's very, very interesting. You can give that a read if you want. And this is one way to resolve hash collisions. It's called open addressing, and this specific thing right here that it's doing is called quadratic probing, where some quadratic polynomial is added to the index every time it finds one that's already occupied. Now there are other ways. For example, there is something called chaining, where you have, instead of a whole bunch of indices, like only one index into whatever value you want to store, what happens is you store a list of linked lists, and every time you get a collision, you add that key value pair to the linked list. And you can search through that in sequence to find the element you're looking for. So, all of these are a part of my HashMap class. Excuse me. And I was able to use that for a very, very short program, which checks if two phrases are anagrams of each other. Now, an anagram is where you take a phrase, rearrange its letters, and then you get another phrase out of it. So how this program works is I have these two functions right here, get letter frequency and get frequency difference. And this get letter frequency right here, this goes through each character in the phrase, converted to lowercase, of course, because the case doesn't matter in an anagram. And if the character is a letter of the alphabet, then we take that key in a hash map and then we add 1 to it. And I have to do this, by the way, just in case the key doesn't exist in the first place. By default, it'll be 0 if it doesn't exist. We add 1, we store that back. And get frequency difference, I do this in the case that the two phrases are not anagrams, and this is how I check how many extra of each letter there are. So I make a shallow copy of the first hash map, and then for every key in the second hash map, if it is in the first hash map, then I take the value and subtract it from the value in the first hash map. And if the difference is negative, I delete that element from the hash map. Otherwise, I store that difference back into the hash map at that position. And then the resulting hash map will be how many more of, whatever letter that is in the first phrase than the second phrase. I hope that made sense, because this actually makes our job really, really easy to check whether or not two phrases are an anagram. So I input a source phrase and a target phrase, and then I pass those to get letter frequency to turn those into hash maps with letters as keys and their counts as values. And I also print those out. And this is where the magic happens. I can compare two hash maps by checking each of their values if they have the same number of keys, and if each of those keys has the same value in both of them. And that, by the way, I believe is in right here. So, you can go through that if you want, but if the source map is equal to the target map, congratulations, these phrases are anagrams. Otherwise, these phrases are not anagrams, and I get however many extra letters that the source phrase has and the target phrase has, and I output them like this. Like, say there's 1 extra P, 2 extra Qs, stuff like that. So, let's test this out. So, let's enter a source phrase, alive, and as you can see right here, there is 1A, 1L, 1I, 1V, 1E. And this is an anagram that I like of it, la vie. That's French for the life. And there's 1L, 1A, 1V, 1I, and 1E in there as well. And congratulations, these phrases are anagrams. Now, let's try this with two phrases that definitely aren't anagrams, like pudding and prestidigitation. So, these phrases are not anagrams. The source phrase, pudding, has 1 extra U and 1 extra D. So, that's too bad. And the target phrase has 1 extra R, 1 extra E, 1 extra S, 3 extra T's, 3 extra I's, 1 extra A, and 1 extra O. And by the way, as a result of how I was able to implement this dictionary, all of these are in insertion order. So, these are coming out in the order in which they were inserted into the hash maps in the first place. So I think that's kind of cool. Now, let's do a little bit more. So, there's this opera writer called Giovanni Pergolesi, and there's this anagram that I really like of his name. First, let's try I love opera, and I'm not gonna write the last word because I'm gonna show you what happens when there isn't any extra letters in one phrase, but there is extra letters in the other. So, these phrases are not anagrams. Giovanni Pergolesi has 2 extra G's, 2 extra I's, 2 extra N's, and 1 extra S. And the target phrase doesn't have any extra letters, but it does use some subset of letters from the source phrase. Now, let's actually finish this up. Giovanni Pergolesi is an anagram of I love opera singing. These phrases are anagrams. Lovely. Now, I'm going to do one more anagram, and I'm kind of proud of it, even though it's not exactly the most flattering anagram out there. So, Milwaukee Area Technical College is an anagram for we come in a lecture hall like a cage. I accidentally did a backslash in there, but that doesn't count for the anagram. So, Milwaukee Area Technical College, we come in a lecture hall like a cage. These phrases are anagrams. Congratulations. Try to tell that to a lecturer. See how they react. All right. So I'm pretty proud of this, and I'm very, very interested in anagrams. There are like a whole lot of really, really good ones out there, like dormitory and dirty room, schoolmaster and the classroom, stuff like that. And if you ever want to look them up, they are really, really interesting. I would recommend it. So, I cannot wait to start on my final project. I've already actually done a sort of a demo of it, and I cannot wait to show you once I'm finished with it. Take care.